Hi guys, let's dig in on the cross product and the Lorentz force. So far we've talked basically qualitatively about how um, the magnetic force on a charge is equal to QV cross B. And we had looked at some qualitative scenarios like, if you have a magnetic field um, and you have a charge that's flying through that with some velocity, that you can find the force on that charge using the right-hand rule, at least qualitatively. And we looked at situations. So in this case, you'd point your fingers to the right, and you'd curl them into the page because the magnetic field is pointed into the page, and you would find that the force would be pointed up, and that would be the direction that your thumb would be pointing. Just as a quick qualitative example, um, to connect with what we had been doing before. Um, but what we'd like to do is to be a little bit more quantitative and deal with the situation where these things are not at right angles. So one ingredient that we can add to this is we can recognize that this also is this. We can say this is the same thing as QVB sine theta. And this is useful, if you have a situation where you can specify V and, well, actually, let me put these in color just to kind of keep consistent here. If your problem is specified such that you can see the angle and the magnetic field, or I should say the angle between the velocity and the magnetic field, then you could solve problems with this expression. But more often than not, what happens is your vectors for V and B are not expressed like this. They're expressed as components. So, and in that case, we have to evaluate the cross product. So let's look at the cross product for a second. So as an aside, and this is really a mathematical operation that we have to get up to speed on. So recall that you can specify vectors like this as components, Cartesian coordinates, and we use the unit vector convention I hat, j hat, and k hat to indicate x, y, and z directions. So for example, we could, just specify a couple generic vectors, a and b, by their components. And if you want to take the cross product between these two vectors, how we often do this is to create a determinant where basically just to organize them like this. And how you evaluate this is you look at the diagonals of this thing. So let me see if I can try and put some color in here to help you keep track. So you look at the diagonals. So it looks sort of like, try and draw this as nicely as I can. You would have one that would look like this, one that would look like this, and oops, this, and then one that would look like this. And then that would correspond to I hat times AYBZ plus J hat times AZBX plus K hat times AXBY. And from that, you're going to subtract the diagonals going the other way, which would look let me try and draw this here. Kind of like this. So this would look like k hat times aybx minus j hat times axbz and minus I hat times azby. And this would be when you compute this all out and consolidate the common components, this would give you the cross product, the vector. Remember, cross product generates a vector that would correspond to A cross B. And this is, just sort of the general form for doing this. And, we can confirm some, simple examples that we had already looked at. Like, suppose your A, actually, let me make this black here. Suppose your A vector was exclusively in the x direction. And suppose your B vector was exclusively in the y direction. You can see just by looking at this, so in other words, plus 0, j plus 0, k. You get the idea. And 0k. You can see that, most of these terms would die, like they would be 0, when you go to take the cross product. And all that you would be left with is the terms that have both ax and by. So you can see we would have k hat times ax by. And so if we were doing our right-hand rule, this is telling you that if A is in x and you cross it into B that is in y, then the result of that would be in the k direction. And one other thing that I wanted to note here is, in just sort of a general issue with computing these cross products, is if you were to instead have computed B cross A, now granted I don't have the terms written out like this, you would find, if you were to work this out yourself, that you would get negative ax by. And this is just a word of caution. The cross product is not commutative. That is to say that A is not equal to B cross A. So this is, if we're not familiar with the cross product, that can be a little bit of a problem. And just keep that in mind. You'll pick up a negative sign if you reverse the order of things. And you can kind of visualize this in terms of our magnetic, these magnetic field type interactions as switching the direction of the current or something like that. You're going to get a negative sign. Okay, so that's kind of the general approach for how you would evaluate a cross product. Let's look at a couple example problems where you can see this in more in terms of the physics that we're talking about. So let me give you an example. We're going to have a proton. This is an example. Proton moving with velocity 2 I hat. Let's get this shows a line here. Minus 4 j hat plus k hat meters per second. And it's moving through a magnetic field given by I hat plus 2 minus 3 k hat Tesla. And we want to find the force and find the magnitude of the force. Okay, so we know that the force will be given by the Lorentz force, QV cross B. And we can evaluate this just like we've been doing with the determinant, or I showed you with sort of the general case. So our V pieces, we would have 2, -4, 1. And our B pieces, we would have 1, 2, and -3. Actually, let me make this nice and even. Okay, so what would this look like? Well, I'm just going to keep the Q out here. You'd have I hat times product of -4 times -3 plus J times 2 times 2. So you see, yeah, the J times, oh wait, no, that's not right. Sorry, J times 1 times 1 plus our K hat times 2 times 2. And then we would have the negative pieces. We would have minus a K hat times 4 times 1 minus J hat times 2 times -3, and then minus an I hat times 1 times 2. Okay, so I realize this is kind of tedious, but I wanted to show you it in all the the details, at least a time or two, so you would have some examples to refer to. So we can then consolidate this. Let's put together all the pieces that are the same, or that have the same unit vector. So this would be I hat times 12. There's also an I hat down here, -2, plus J hat times 1. And we also have a factor of minus -6, so this would become +6. And we also have K hat times 4 plus 4. Okay. So really the force, when we boil this down, would look like Q times 10, or let me put it like this: 10 plus 7 J hat plus 8 K hat. So this is our force, and we could factor through the factor of Q, which would be, for a proton, it would be positive 1.602 times 10 to the minus 19. And this would be, the force written in component parts. So that's what we were looking for. And you can notice we picked numbers that were small, just so that it would be kind of easy to show the multiplication. If we actually multiply this out, it's very small. But let's do that to figure out the magnitude. Let's figure out what the actual magnitude in newtons would be. So if we want the magnitude of this, we can think of this as, in 3D, it's, 10 along x, and then 7 along y, whatever that would look like, and then 8 along z. So we need to find, that's not a very good picture. We need to find the length of this vector. And to do that, you can use the Pythagorean theorem. So in 3 dimensions, so this would look like the square root of, q squared times the square of each of these components. So we could factor out actually the q, and then you'd be left with the square root of 10 squared plus 7 squared plus 8 squared. And this would look like q times 14.6 or so. And if we actually multiply this out, 1.602 times 10 to the minus 19 times 14.6, we would find that this is a ludicrously small number of 2.3 times 10 to the minus 18 newtons. So that's the magnitude of the force. Let me just put this here. And that's the number that we get if we multiply, actually evaluate and find the length of that force vector, find the magnitude of the force vector. So hopefully this example kind of shows you this cross product in action. I think this is the type of thing you definitely have to practice for yourself to get comfortable with it. And there's a couple problems in the homework that ask you to do this kind of thing. So you'll get a chance to practice. And I think I noticed in your surveys more examples would be good, so I'll put together another example for this topic as well. So let me show you another example. Come on, pen. So for this example, consider we have an electron, and it experiences a force. So this is actually a question out of your textbook, number 26. And this is kind of a nice question because rather than finding the force, we're going to find the velocity. We're going to solve for something else. So an electron experiences a force (3.8 I hat minus 2.7 j hat times 10 to the minus 13 newtons. And this occurs while passing through a magnetic field. Where our magnetic field is 0.85 Tesla in the k hat direction. And we want to know what is the velocity of the electron. I.e., what are dx, dy, dz. So let's set this up. We know that the force on the charge is going to be qv cross b. And we've been given the b, and we've been given the force. So we're looking for the velocity. So what we'll do is we'll evaluate the determinant and come up with the components and then scrutinize the components to figure out what the velocity is. So in other words, we're talking about an electron now. So we'll have negative E times now our V components, I'll just put them in as variables because we don't know what they are. And then in terms of the magnetic field, notice some of these are going to be 0 because the magnetic field is only aligned or is aligned along Z. So we have that. And then we can evaluate this like we did before. So what components are we going to have? We'll have I hat times Vy times 0.85 plus J hat, notice that'll be Vz times 0 plus K hat times Vx times 0 minus the other components that we'll have minus K hat times Vy times 0 minus J hat times Vx times 0.85 plus I hat times Vz times 0. So thankfully, a lot of these components are 0, but I put them in just so you could see the process again. Oops, and this would be a minus sign. So what are we left with? We have, well, let's just write it out here. We have that the force, so I'm going to rewrite the force too that we have. Force that we were given was 3.8 times I hat minus 2.7 J hat minus 13 newtons. And that equals 0.85 J hat. And then let's be careful here. So we'll have minus Vx times 0.85 J hat. And we can associate the components. So let's match up the components. We have in oh, wait a second, I made a mistake here. This is I hat. We'll have negative E Vy times 0.85 in I hat, and that has to equal 3.8 times 10 to the minus 13 newtons in I hat. And then we also have the two y pieces, so we'll have positive E Vx times 0.85 J hat, and that has to equal negative 2.7 times 10 to the minus 13 in J hat. And now we have, two expressions, and we can just solve this for Vy and Vx by dividing. So in other words, Vy would give us our 3.8 times 10 to the minus 13 newtons divided by negative E, so negative 1.602 times 10 to the minus 19 times 0.85, and this would give us negative 2.8 times 10 to the 6 meters per second. And then we can do kind of the same thing with the Vx piece. So Vx would be negative 2.7 times 10 to the minus 13 newtons divided by a factor of E, charge of the electron, times our 0.85 Tesla, and we would get about 2, or also negative here, 2 times 10 to the 6 meters per second. So these velocities are a lot more like what we would expect, kind of what we saw in the lab, right? It was pretty easy to accelerate electrons to quite fast in our Teltron tubes. So hopefully this gives you a feel for another kind of problem that you can solve that involves looking at the cross product in components. So it's not just solving for the force. You know, if you have the force, you could also expand this and solve for other unknowns like the velocity. So hopefully this helps you as you work on these kinds of problems.